All right, today we're going to be taking a look at a couple more tests that we can use for series. And, well, these two tests are actually going to be tests for absolute convergence. In some sense, you could really say that these tests are almost redundant because it turns out that these tests are kind of just applications of the comparison tests that we've done, but they come up often enough and they simplify things enough that they're worth thinking about sort of separately, regardless of the fact that, yeah, technically we could just do them using the comparison tests or whatever. So what we're going to be looking at first here is something called the ratio test. Now, the ratio test is a test where we don't, like, in and of itself, we just look at the series itself. So suppose that we have the sum from n equals 1 to infinity. Of course, we could do n equals 0 as well, but I'm going to say n equals 1 just for the sake of this writing it down. And we are summing up these a sub n, this a sub n sequence. So let's let L be equal to the limit as n approaches infinity of the ratio an plus 1 divided by a. So we're looking at the n plus 1 term divided by the n term. Then we have the following conditions. If L is less than 1, then the series is absolutely convergent. And thus it's also convergent. Because remember, one of the things we said about absolute convergence is it implies regular convergence. And that's one of the things that makes this ratio test useful, is that it often tells us something about, it's not simply that we're interested in absolute convergence. Absolute convergence is nice and all, but usually we're really just interested in convergence. The second possibility is that L is equal to 0. Now, I'm sorry, not 0. L is equal to 1. In this case, then the test is inconclusive. We have to use a different sort of method to figure out whether this thing converges, diverges, or it may even be conditionally convergent. Okay, so remember, conditional convergence means the series converges, but it doesn't converge absolutely. And we saw examples of that, like the alternating harmonic series that converge, but they do not converge absolutely. And then the third case here is that we might have L bigger than 1. In this case, the series is going to be divergent. Okay, so why is this true? Well, let's look at a little proof of what is going on here with this ratio test. So keep all of this stuff in mind, but I am going to erase this for the moment so that I've got more space. And now we will look at a proof. So we have 3 different cases to deal with. Let's start off with case 1, where L is going to be strictly less than 1. And we want to show that this thing is absolutely convergent. So note, there is an R with L less than R less than 1. And we can pick such an R because L is less than 1. So there has to be some number between L and 1. Now, the other thing we can notice is that there is a capital N such that if little n is bigger than or equal to capital N, we have the absolute value of an plus 1 divided by an is less than r. Why is this true? Well, the limit of this ratio is L. So for any choice of epsilon, there's a capital N that guarantees we are within epsilon of L. So all I have to do is I just have to pick my epsilon to be smaller than r minus L, and then this condition is going to be guaranteed. So this kind of argument with limits is kind of a standard sort of thing. We often don't write it down explicitly because we use it an awful lot. If you're doing a lot of stuff with limits like this, you end up using it an awful lot. And so you want to get kind of used to making these kinds of arguments. Now, you may not necessarily need to make a lot of these kinds of arguments unless you go on to take a course in analysis, but it's still good to kind of get used to this idea. So I'm not going to write out the details of that, but yes, this follows from the definition of the limit in terms of epsilon and capital N. And the note that I will say is pick epsilon to be smaller than r minus L. And that's really where this is going to be happening. So then what we can say is, notice that we have absolute value of a sub n plus 1 is going to have to be less than r times the absolute value of a sub n. And we also have the absolute value of capital N plus 2 less than r times absolute value a n plus 1. That's going to have to be less than r squared times the absolute value of a sub n. And so on. In fact, what we can say in general is that the absolute value of a n plus k is going to have to be less than r to the k times the absolute value of a capital N. Now, notice I do have to start this process at capital N because I need to guarantee that I have this condition here. Otherwise, this whole thing isn't going to work out. So this is not necessarily true for the first some finite collection of terms at the beginning of the series. But it is going to be true eventually. So now what we can do is we can do a comparison test to a geometric series. And the comparison test we're going to do is the sum from n equals capital N plus k, or y plus k, capital N equals n up to infinity of the sum absolute value of a sub n. Notice this is the capital N. This is now just a fixed number. It is this particular thing in the series. And then we're going to have r to the, I want to make sure that I've got this thing written down correctly, r to the capital N minus lowercase n. Well, this is the same as the sum from n equals 0 to infinity, absolute value a sub n, r to the n. I've just sort of rescaled my index here. But the thing is, we just said that all of the terms are smaller than the terms here. Well, what does that mean? That means that since this converges, being a geometric series with r less than 1, so our series converges as well. Because, we have this condition here. All of the terms in this sequence that we're summing up for this geometric series are bigger than the terms in this n sequence, at least for sufficiently large values of n. So strictly speaking, what we've shown is, let me write this out in a bit more detail. What this means is that the sum from little n equals capital N to infinity of the a sub n's is absolutely convergent. But here's the thing. If I cut off the first finite collection of terms of a series, that doesn't change whether it converges, because that finite collection of terms is just some number that starts off the series. That means that the sum from n equals 1 to infinity over these a sub n's is also absolutely convergent, or the sum from 0 to infinity. Remember, we can always cut off the first few terms or any finite collection of terms, and it doesn't change the convergence. We've actually seen that kind of thing before. In fact, in a previous lecture, I don't remember if it was the last one or the one before that, but we looked at an example where we wanted to apply a certain test that required that the series that we're looking at have decreasing terms. And we said, well, the one that we're actually looking at doesn't have decreasing terms because for the first few terms, the terms were getting bigger. But we were able to say, but in fact, eventually they're decreasing, and that's good enough. Well, similarly here, eventually we get something that can be done with a comparison test to a geometric series, and that is good enough. Now, the second case that I'm going to deal with is actually case 3 rather than case 2, simply because it's so similar. So case 3, L is bigger than 1. Then there is an R with 1 less than R less than L, and there is a capital N with, when little n is bigger than or equal to capital N, absolute value of A sub n plus 1 divided by A sub n is going to be bigger than R. Once again, you're just going to pick an epsilon that is smaller than this time L minus R, and you get this result. Okay, from here on out, this is almost identical to case 1, so I'm not going to write out all of the details for you. If you're really interested in seeing all the details written out, you can work them out yourself pretty easily, or you can check, there's plenty of sources that will give you all the details. But literally, the proof at this point is almost the same. So the thing is, we now do a comparison to the sum from n equals capital N to infinity of absolute value of A sub n, R to the n minus n. This is a geometric series with R bigger than 1, so it diverges. But by the comparison test, that means that our series diverges as well. Now, in fact, what we can say is something a bit more than this. What we can actually say is that this really implies even more than this. We can say the limit as n goes to infinity of the A sub n's is not equal to 0, because if these are converging to something bigger than 1, then this limit cannot be equal to 0. And because of this, by the divergence test, this means that not only is our series not going to be absolutely convergent, it's actually going to diverge as well. So I guess I said it was similar to the first case. It's actually a little bit different. It's almost easier than the first case because we just go to this fact and then we use the divergence test. Remember, if the limit of the sequence that you're summing isn't 0, then the series cannot converge. Now, the final case is case 2. And case 2 is going to be left as a little bit of an exercise for you, although it's not a super complicated thing or anything. So I expect it'll only take a minute for you. So the case 2 is if L is equal to 1, then anything can happen. And here are some examples that show that anything can happen. If you have the sum from n equals 1 to infinity of 1 over n squared, this is absolutely convergent. But it also has L equals 1 if you try to do the ratio test. If you do the sum from n equals 1 to infinity of the alternating harmonic series minus 1 to the n over n, this is conditionally convergent, and it also has an L equals 1 ratio test. And finally, if you do the regular harmonic series, this is divergent, but it still has L equals 1. So I will leave it to you to check. Actually, we've already checked these three things. Technically, you can just go back and see what we did to check these. but each of these is quite straightforward to check. This one you do with an integral test. This one you do with an integral test. This one in the middle you do with the alternating series test. So, like I said, we've actually done these before, but if you don't remember or whatever, probably a good idea to take a minute, think about each of these and make sure you understand how to verify them. So in this case too, the ratio test is not actually useful. It does not actually do anything for us. So let's take a look at some examples here of doing this kind of thing. So here is one that is possible to do by using one of these tests. Let's suppose that I have the sum from n equals 1 to infinity, and let's suppose here that we have 10 to the n divided by 4 to the 2n plus 1 multiplied by n plus 1. Now, I'm going to say that when I look at this, I sort of expect this thing to converge. The reason I kind of expect this thing to converge is because on the top, I have an exponential whose power is n. On the bottom, I have an exponential whose power is 2n plus 1. And in some sense, that exponential with a power of 2n plus 1 is going to grow way faster than something that's an exponential with just a power of n. You might think that seems a bit weird, but, well, it kind of depends upon what the bases are as well. So we do need to be more careful than what I just said. And that's why we need the ratio test, because intuitively, when I look at this, I sort of expect convergence, but it's not necessarily easy to just see that it converges automatically. There are ways that we could do it, though, because, for instance, we could write, well, 10 to the n is actually 4 to the n times the log base 4 of 10, and we could probably just do it by using this technique. The problem with doing this is, like, intuitively, this is why I expect this, because log base 4 of 10 is smaller than 2. So this looks, the terms here are something that is like 4 to the an over 4 to the 2n plus 1, where a is smaller than 2. So it looks like this should kind of converge. Plus we've got that n plus 1 down here to deal with. It looks like this should converge, but the problem is, what is a exactly? We don't know. Anyway, we could do it this way and then use a comparison test. It actually wouldn't be too bad to do. But I want to show you how to do it by using the ratio test. So that was a bit of a tangent here where I was just talking about how you can kind of do it other ways. But yeah, let's take a look at the ratio test. So let's look at limit as n approaches infinity of an plus 1 divided by an absolute value. Now, in this case, we don't even really need to worry about the absolute value because all of these terms are positive. If maybe we had some negative terms thrown in here, maybe we have like a minus 1 to the n as well, then we would have to take the absolute, it would be more work to take the absolute value, but it really wouldn't change the problem that much at all. Well, this is going to be the same, and this is a little trick for writing these things out that can often help. This is an plus 1 times the reciprocal of an. The reason I'm going to write it this way is because it's just going to save me a bunch of space. It's not like this is really an essential mathematical step, but it keeps me from having to write insanely large compound fractions. And I don't want to write insanely large compound fractions, and I doubt you do either. So in this case, an plus 1, this is going to be 10 to the n plus 1 divided by 4 to the 2n plus 3 times n plus 3. Sorry, that doesn't even look like a 3. And then we're multiplying by the reciprocal, which is going to be 4 to the 2n plus 1, n plus 1, divided by 10 to the n. Okay, so we can simplify this. This is the limit as n approaches infinity of, why am I suddenly so confused here? We're going to have a 10 in the numerator, and in the denominator, we're going to have a 4 to the squared, and then we have times n plus 1 over n plus 3. There we go. I don't know why that was so confusing to me for a minute there, but somehow my brain decided algebra was no longer a thing it was going to do. Okay, well, the n plus 1 over n plus 3, this just goes to 1 as n goes to infinity. So this limit becomes 10 over 16, which is definitely less than 1. And that shows us that this sequence is actually absolutely convergent, and hence it is convergent. Okay, so that was actually not too bad, right? I mean, apart from the fact that for a minute there, I decided not to be able to do algebra anymore, this was actually a fairly straightforward calculation to do. And that's what's really nice about this ratio test, okay? It makes you, in a lot of situations, it really does make things, in some sense, easier, okay? And so that is sort of a nice feature here. So let me show you another example here, and give me just a second while I bring it up. Sorry, it took me just a second to get this, but yeah. So let's take a look at the sum from n equals 1 to infinity of 3 to the n divided by n factorial. Now, just in case it's been a while for you since you've done factorials, let me remind you what a factorial is. So n factorial is equal to n times n minus 1 times n minus 2, all the way down to 2 times 1. So we just multiply all of these numbers here. And for the case of 0, we define 0 factorial to be equal to 1. That's sort of a special case. The reason we do this, by the way, is because usually we define this with what is called a recursive formula. So we say 0 factorial is equal to 1, and then we say k plus 1 factorial is equal to k plus 1 times k factorial. And so starting off with 0 factorial being equals to 1 ends up giving us this formula. Anyway, that's neither here nor there. That's just, I'm mentioning that because obviously we need to know how to write this thing out in order to deal with this problem. Now, this would be a little bit of a tricky problem to deal with in some ways because the factorial function is a bit of a funny function. You can generalize it to the real numbers. This is what the gamma function does. So we could try to look at things involving these limits by using calculus, but it's not really straightforward. The gamma function is not easy to work with. And otherwise, it is only defined for these positive integers. So it's kind of got this major limitation here. That would make things a little bit tricky to use some of the tests on. But fortunately, the ratio test is going to give us this whole thing in a very straightforward manner. So what we're going to do is we're going to say, okay, my a sub n here is 3 to the n over n factorial. In fact, to make things more interesting, why don't we do minus 3 to the n? Just so that we have a minus going on here. And it's not going to change the problem appreciably at all, but I want to show you what happens. So here's my a sub n, and then what I'm going to do is I'm going to look at the limit as n goes to infinity of the absolute value of a sub n plus 1 times 1 over a sub n. In fact, why don't you pause this for a moment and see if you can figure this out for yourselves. It's not actually as bad as you might worry it's going to be. Things really do cancel in a fairly nice manner. Okay, were you able to figure it out? I don't know if you'll be able to figure it out or not. You may not be used to working with factorials, but it's really not super bad here to work with, because what is this going to be? This is going to be the limit as n goes to infinity of the absolute value of minus 3 to the n plus 1 divided by n plus 1 factorial times n factorial over minus 3 to the n plus nothing, actually. Now, here is the key step. And if you were able to figure out this step yourselves, then you'd be all set. If you didn't figure out this step, you'd be really stuck. The key observation is n factorial divided by n plus 1 factorial this is n times n minus 1 times all the way down to 2 times 1 divided by n plus 1 times n minus 1 all the way down to 2 times 1. Well, every single thing cancels except for the n plus 1 in the denominator. So this is going to become the absolute value of negative 3 divided by n plus 1. The negative 3, of course, just comes from canceling this n plus 1 with this n exponents and everything. Well, this limit is actually equal to 0. And that means that our original series is absolutely convergent, and therefore it is also convergent. So there we go. If you were able to figure this out, congratulations. If not, don't worry too much about it. Just make sure you understand how to do it now, because this kind of technique is actually going to become really, really useful for us. See, doing limits of series, or I should say doing infinite series like this, these kinds of infinite series that involve factorials like this are actually super useful. As we will see next week, when we get something called a Taylor series is a way of describing a function in terms of a series. And it turns out that the formula for the Taylor series involves factorials like this. So being able to deal with these kinds of series is actually going to be something that we want to get really, really good at. And fortunately, this ratio test is a nice way of doing it. Okay, so that's one of the things that we are sort of moving towards. Now, there's something else that I want to talk about today before we move on to talking about those Taylor series and things next week. So the next thing I'd like to talk about here is another test that you can use, and this is known as the root test. Now, once again, the root test is sort of one of these things that it very much is sort of just like the comparison tests in an applied manner. So let's consider that we have the sum n equals 1 to infinity of a sub n. And we are going to say, let's let L be equal to the limit as n goes to infinity of the absolute value of a sub n raised to the 1 over n. In other words, the nth root of this absolute value. Then this is going to seem very familiar because we just saw the ratio test, and this is fairly similar. If L is less than 1, our series is absolutely convergent. If L is equal to 1, our test is inconclusive. And if L is bigger than 1, then our series is going to be divergent. The proof is really very, very similar in a lot of ways to our proof of the ratio test. Okay, so take a moment, make sure you've got this written down. We're going to start talking about proving it. So kind of like the proof of the ratio test, we're going to want to make a comparison test here. So what we can say is that once again, in case 1, where L is less than 1, there is an R with L less than R less than 1. Okay? Same as the thing that we did before. And just like we did before, there is a capital N with little n being bigger than or equal to capital N, implying that the absolute value of A sub n to the 1 over n is going to be less than R. Again, pick epsilon to be equal to R minus L and apply the definition of the limit. This is, like I said, it's a standard kind of argument that people make all the time. If our limit is L, then we can get sufficiently close to L. That means if L is less than R, eventually everything has to be less than R. Well, at this point, maybe you can kind of see where I'm going with this. You may even want to see if you can finish off the proof yourselves if you're feeling particularly ambitious. Because what we're going to do is we're going to do a comparison test that's almost the same as our comparison test with the ratio test. Why in the world did it take me like 20 seconds to remember the name ratio test there? Apparently I was having some sort of a momentary lapse. Anyway, so the idea here is we're going to do a comparison with the sum from n equals 1 to infinity of r to the n, which is, of course, going to be a geometric series that converges. Now, the thing that we know is that absolute value of an raised to the 1 over n is going to be less than r whenever n is bigger than or equal to capital N. So the absolute value of a sub n is going to be less than r to the n when n is bigger than or equal to capital N. But if we just cut off the series now and start it at capital N, this is just a part of a geometric series with the first finite number of terms cut off. And therefore, this converges, and thus the sum from n equals capital N to infinity, absolute value of a sub n, converges. But that means that our original series has to be absolutely convergent. Because the series, if we cut off the first finite number of terms, we get absolute convergence. And cutting off the first finite number of terms up to capital N does not change whether or not things converge. So there we go. We have our result. Like I said, very similar to the ratio test. The other cases are also similar to the ratio test. So I'm not going to say all the details of them. I'm going to kind of leave some of the details out here. In case 3, where L is bigger than 1, once again, we end up showing that the limit as n goes to infinity of the a sub n's is not equal to 0. And it can't be, because if it were, then we would end up with the root test not coming out to be L bigger than 1. So I'm not going to show you the details of this. If you want to see the details, they're on Paul's math notes, and you can take a look there. But it's very similar to the ratio test. I don't think it's going to be particularly enlightening. And finally, for case 2, where L is equal to 0, you can kind of use similar examples to last time. So if L comes out to be equal to 0, then we can consider the sum of 1 over n squared, the sum of minus 1 to the n over n, and the sum of 1 over n. And we get all 3 possibilities. We get absolute convergence, conditional convergence, and divergence. Why did I say L equals 0? I'm so sorry. L equals 1 is case 2. So the only tricky part here maybe is to show that this L really is equal to 1 for each of these series. I will leave that to you as a little bit of an exercise to do yourselves. So it's really, it's similar to what we said with the ratio test, right? So not anything that's huge new stuff. So let's just take a quick look at using the root test in a particular example. Let's suppose that we want to decide whether the sum from n equals 1 up to infinity of, let's say that we have the following. Let's suppose that we have 3n minus 2 divided by 2n squared plus 3. And then this whole thing is raised to the nth power. This is a perfect example of where the root test can become really, really useful, okay? And the reason, or actually, sorry, I've become moderately confused. I am unconfused. I'm so sorry. Looking at my notes, things moderately confused me for a moment. The problem has gone away. So from the root test, if I look at the limit as n approaches infinity of the absolute value of 3n minus 2 divided by 2n squared plus 3 raised to the n, raised to the 1 over n, the root test works great here because it gets rid of the variable or the index in my exponent. And this is actually going to become limit as n goes to infinity. Now in this case, I can get rid of the absolute value. There's no negatives to worry about. So I can just say this is the same as the limit as n goes to infinity of 3n minus 2 divided by 2n squared plus 3. Well, this is equal to 0. So in fact, our series is absolutely convergent. Now, here's one that you can do with the root test. That's a tiny bit trickier. Still not too bad, though. Let's suppose that I want to do the sum from n equals 1 to infinity of, maybe I have negative 3, or let's say I have 1 minus 3n squared divided by 5n squared plus 2n, and all of this is being raised to the nth power. This one is a little less intuitive. See, in that previous example, the numerator was a lower power than the denominator, and so raising the thing to the nth power, you would still kind of expect everything to work out the same. But in this case, it's not quite as straightforward to see what's going on. Well, let's take a look at the limit as n approaches infinity of absolute value 1 minus 3n squared divided by 5n squared plus 2n, nth power 1 over n. So what this is going to come out to be, now we need to be a little bit careful here about our signs. The numerator is going to give me always a negative number. So I need to switch the sign to 3n squared minus 1. The denominator is still always going to be 5n squared plus 2n. And then I can cancel off the n and the 1 over n's here. So I'm not sure how well my explanation actually made sense. But take a moment and make sure you see where this comes from. And I flipped the sign around because of this absolute value business going on. Well, the limit as n goes to infinity of this thing is going to be equal to 3 over 5. That is less than 1, so we get absolute convergence and hence convergence. Now let me give you a quick example to think about yourselves here for a moment, and we'll see what ends up happening with this one. Let's suppose that you have the sum from n equals 1 to infinity of 4n cubed minus n divided by, let's say, n minus 3n cubed, all raised to the nth power. Take a moment and see if you can use the root test on this one. So did you figure it out? It's kind of similar to the previous example. If I look at the limit as n goes to infinity, absolute value of 4n cubed minus n minus 3n cubed raised to the nth raised to the 1 over n. I need to be careful about signs here once again. So the denominator is going to give me 3n cubed minus n. The numerator is going to give me 4n cubed minus n. Then the 1 over n and the n cancel with each other. This limit is going to be equal to 4/3. This is bigger than 1, so the series diverges. Okay, so I've shown you a few examples here of using the root test. There are other situations where the root test becomes useful as well, and you may want to take a look at some of those examples both in your book and on Paul's math notes. Now, you might wonder, what about in the case where L is equal to 1? Can we go back to using the ratio test? Unfortunately, it turns out that in a lot of situations, if the root test gives us L equals 1, the ratio test ends up giving us L equals 1 as well. So yeah, there's problems going on there. Maybe, I'm not going to say it'll never work. It might work sometimes where you can use the ratio test but not the root test or something like that. I'm just saying, don't expect that to happen too often. So when one of these tests fails, it's often the case that we end up in a really tricky situation and we're not entirely sure what to do. But there we go. These are some examples of other tests. Now, the general strategy for figuring out whether series converge or diverge, it's sort of like the stuff that we said about integration. You just kind of get used to certain patterns. Like when I see the fact that everything is raised to the n, that probably means I want to do a root test. Or maybe this would be raised to the 2n. Well, the root test would still get rid of that thing, the fact that the index shows up as an exponent like that. So it would still help me simplify things. The ratio test is very useful, especially if you see things like factorials showing up. And in terms of comparison tests or limit comparison tests, well, those are sort of, if you see something that is an easy comparison, or if you see something where, oh yeah, this will form a nice ratio with a known series, then you want to use those approaches. So it's kind of one of those things where you just have to get used to the different patterns involved. In my opinion, it's not quite as complicated as recognizing the patterns for integration, but it's still kind of annoying. So this is definitely one of those things where you're going to want to look at a bunch of examples and you're going to want to practice a bunch yourself, okay? Now, where we're going to go with this is next week, we're going to take a look at what are known as power series, which are series that define functions. There's actually many ways to define functions using series. Essentially, what you do is, instead of just summing up a sequence that only depends on the index, you also put something in there that depends upon some variable. Well, it turns out that although this might sound like kind of a weird thing to do initially, it turns out to be one of the most useful things we can do in mathematics, at least within a certain sort of field of application. So we will study these power series, we will look at the properties that they have, we will look at the kinds of functions that they define, and yeah, we will kind of go from there. Now, we've already sort of seen an example of this. So the example we sort of saw, and you can go back and check this out, is we used a geometric series to represent 1 over 1 minus r, right? Geometric series came out, well, technically they came out to be a times 1 over 1 minus r. But this is actually, this came out as the answer to what some series sums up to. And so you can represent this function as a geometric series. And then you can think of this as a function of r. And then the geometric series represents this function. Well, in general, it might be somewhat tricky to say what a power series is equal to. We may not be able to give quite such a neat answer, but as we will see, they can still be very useful. And then we will ask the question, given a function, is there a way to represent that function as a power series? And the answer is often yes, at least for nice functions, like the sorts of functions that we often work with. Although the answer is also sometimes no. And there can be very interesting functions that are not representable by power series as well. So you do have to be a little bit careful there. But anyway, we'll get into all of that next week. And we'll go over all of this stuff in detail.